So no matter what this function is now, it doesn't matter. The fact that we could anti-differentiate this and get tangent inverse t would have been nice if we'd have had to do it to the old way. But can you see in the new way it doesn't matter. And if this is if this is a function which we can't anti-differentiate, which honestly is most of them, then this still works. Agreed? So this is a nice thing. Let's look at another one. We got a little problem in this one. Anybody notice what it is? Got an x squared up here, right? That's kind of messing us up a little bit. So how are we going to deal with this x squared? Well, we've had to deal with situations involving this kind of thing before last semester, right? I'm taking the derivative, but now instead of having an x, I have an x squared. Can anyone think of a sort of analogous situation that we dealt with last semester that was like this? Dylan? Yeah, effectively. And what were we doing in doing that? What rule? Yeah, there you go. It was the D box, which is what rule? Chain rule, right? That's how we dealt with that. If I asked you to take the derivative of, I don't know, sine x, you all say cosine x, right? You all got that, right? If I ask you to take the derivative of sine x, you say cosine x, no problem. If I ask you to take the derivative of sine brackets x squared, you don't say cosine x squared. You say 2x cosine x squared, right? You got the D box thing happening, right? The chain rule thing happening. We do the same thing here. We have a problem in that the upper limit of integration does not match the derivative. But we can use the chain rule to take care of that. So, anyone want to hazard a guess? What do you think the answer to this thing is going to be? I mean, first of all, everything else is okay with this, right? We do have the derivative of an integral. We do have the lower limit of integration as a constant. Anyone want to hazard a guess? What do you think this is going to become? Almost. There you go. Same rule as before, right? The x squared goes in, and we multiply by the derivative of x squared now. We got to take into the consideration the fact, because we're dealing with a rate of change here, this is a derivative, we have to consider not only how is the integral changing, but how is the x squared changing, okay, which is where the chain rule comes from. So we take that into consideration by saying, okay, well, we'll consider that by taking the derivative of x squared, which of course is 2x, and we probably rewrite that as 2x cosine x squared. Remember I told you there are 4 situations? That's situation 2. Situation 1 is the one where everything's perfect, and we just put the x in. Situation 2 is the one where we got everything we want except we have a function of x up here instead of an x. And then we use the chain rule, right? Whatever this function of x is goes in for all the t's, and then at the end we multiply by the derivative of it. Can you see it doesn't really matter particularly what we have up here anymore, right? If this was a sine x or an x to the 27th or whatever variable, whatever I want, it doesn't matter. We just have to be able to take the derivative of it, and we're all good at that. Everybody okay? Situation 2. Situation 3. Can you see here, again, we have a little problem here, don't we? What's the problem this time? What's backwards? Yeah, the limits of integration are upside down, right? The lower limit of integration is not a constant, but the upper limit is, right? I would be really, really happy if the x and the 5 were reversed. Then I'd have situation 1, what I just dealt with, right? Life would be great. But they're not. But we can deal with this. Anyone? How do we deal with this? Benitez? Yeah. Remember the properties of integrals that we dealt with a couple of days ago? The integral of from a to b of f at x is the same as the negative of the integral from b to a. So if I really want the 5 on the bottom, I put it there and I just make the thing negative. And so I can change the sign of the integral and reverse the limits, and I get that. And now I've got situation 1. Agreed? Everybody write down your answer. an answer? No. You're being too complicated.
Mm-hmm.
You reverse the limits of integration,
Mm-hmm.
and you just put the x in. Yep. Here? Yep. Is that a negative? Yeah. Okay, so everybody's pretty well got it. Right? We just do the same thing as before. The x goes in, we're done. Piece of cake. Okay? The derivative and the integral effectively cancel each other out, and we're just left with the same function except with a change of variable. Everybody okay with that? Remember I told you there were 4 situations? We've now dealt with 3 of them. Okay, situation 1 is the nice easy one where everything goes the way we want. Situation 2 is where we've got a lower limit of integration, which is a constant, but the upper limit is a function of x instead of being an x. Situation 3 is where we got the x in the wrong spot. Can you see, by the way, what if this was an x cubed? Yeah, it would kind of be a combination of this and the situation before, right? We'd make it a negative, the x cubed would come up, and we'd end up with a 3x squared out in front. Okay? Now we got situation 4. This is the ugliest one. What's the problem here? You don't have a constant anywhere, right? Which is a big deal because remember what the rules say. Number 1, I need derivative of an integral. I got that. Number 2 says that the variable of differentiation has to match the upper limit. I'm okay with that. But rule 3 says that my bottom limit has to be a constant, and it's not. And I also don't have a constant in the top limit, so I can't reverse them. Any ideas how we might deal with this? Again, I'm going to ask you to think back a few days ago to what we were talking about with the properties of integrals. Could do that. I mean, I'm not sure if we're going to be able to get the antiderivative of 1 over 2 plus e to the t. But you're right, we could try that. That would maybe give us an answer. But I would like to try and figure out a way of muscling this into part 1 of the fundamental theorem. Do any of those properties of integrals that we dealt with a few days ago help us here? Maybe when I split it. Remember that one? I like where you're going there. Can you keep going with that? Let's go back first. Before we even think about this one, let's think about what that rule was. Okay, let's go back for everyone else and just think about what that rule was. That rule said if I have the integral from a to b, I can write integral from a to b equals, anyone? Right. Remember? Integral from a to c plus integral from c to b. Doesn't even matter if c is in the middle. Right? How is that going to help me here? Integral from 2x to x squared. Keep going, Anna. Integral from 2x to x squared equals integral from 2x to, so choose, 4. Plus, there you go. That'd work, wouldn't it? Is that true? Is that a legal move? Sure. Let's think about that for a minute. Our problem here is neither limit is a constant. So we split the integral into 2 parts. Anna chose 4. I chose 0. It doesn't matter what constant we use, it says. Anyone tell me why? Why? Because you will reverse it the derivative of? Sure. The derivative of a constant is 0. It doesn't matter. Remember the first example we did? I said we were sort of lucky that we had a minus pi because the sign of minus pi was 0, right? Then we looked at it and said, no, we weren't lucky. It didn't really matter. Same is true here, right? Anna said 4. If I put 4s in here, what changes? Nothing. Because when I put a 4 into this, I'm going to get a constant. The derivative of a constant is 0. When I put a 4 in here, I'm going to get a constant. Derivative of a constant is 0. Doesn't matter what constant we pick. Okay? So this is good. Now, are we there? Not quite. What do I got to do now? Yeah, this is still not legal, right? So how do I deal with that? Sure. Reverse the limits and deal with the negative. We already did that. And now I have situation 2 and situation 3 kind of combined here, right? Can everybody write down your answer to this, please? Yeah, you got it. E to the x. That goes in e to the 2x. Right? And then 2, yeah, you're right. There you go. Good. Yep. Yep. Good. Yeah, everybody's all over this. The rule itself, fairly straightforward. Remember what it says. We take the 2x and shove it in everywhere we see a t, and then multiply by 2. And here, we take an x squared, shove it in everywhere we see a t, and then multiply by 2x. And we get that. Which we probably clean up a little bit. We probably put the positive term first. We probably put the 2x and the 2 in the numerator. We probably end up with this. Okay, which is what you all ended up with. Everybody good with that? Yeah? That's situation 4. That's as bad as it gets. Okay? It's never going to get worse than that because really it can't. Okay? So we can see now it doesn't particularly matter whether we got a constant in the top or the bottom. In fact, it doesn't even matter if we don't have a constant because we can make one. And it doesn't matter if we don't have x's. If we've got functions of x, we're okay with that. We can now deal with every situation. Everybody feel good with those 4 situations? Okay. So, fundamental theorem of calculus part 2. This is the one we learned a couple of days ago. The integral evaluation theorem. Okay, remember? Integral from a to b says take the antiderivative, shove in a b, shove in an a, subtract. That's part 2. We combine this with part 1. We already knew this. Okay? We combine this with part 1, and we've now got the fundamental theorem of calculus, which arguably may be one of the most important theories in the history of mathematics. A really big deal, this one. Okay? So the whole thing put together looks like that. Part 1 is what we did today. Says if f is continuous on AB and big F is written as this area getter function, then this has a derivative, and the derivative is the function evaluated at the upper limit of integration. That's what we just did. Part 2 says how to evaluate an integral, and it just says that what we do is take the antiderivative, put in b, put in a, and subtract. Those two things together are called the fundamental theorem of calculus, and that's kind of what the whole second part of the semester hinges on. Okay, so this is what we're going to be using for the next couple of months. All right, back to the note. So, we've looked at how do we get the right answers. We've looked at these 4 situations. Yes? Now, we need to think about what does it mean. In other words, what are these answers that we're getting telling us? All right. So let's start by looking at a geometric interpretation. In fact, really that's the only thing we're going to look at today. In a couple of days I'll get around to talking about the algebraic interpretation, which is really much the same thing. But I think geometrically this is a lot easier to see what's going on. That's what the theorem says. Remember? Okay? Derivative of an integral, variable of differentiation matches the upper limit of integration, lower limit of integration is a constant. What do? We replace the t with an x and we get that. Okay? That's what the theorem says. Now we want to think about what it means. So let's start with this. What is this part in red? Just ignore all the black, just look at the part in red. What does that mean? Okay, keep going. And the x-axis? If I got f at t? And the t-axis. I would have to have a t-axis now, right? So this is going to give me the net signed area between the curve f at t and the t-axis. Finish it off. From a to x. This is very much like what we've been doing. One significant difference is that, yeah, x is a variable. If I asked you to draw this thing in red, could you do it? I think so, right? Wouldn't your diagram look pretty much like this? Oh, sorry, hang on a minute. Got to reset this from the last class. Your diagram would look pretty much like this. Agreed? Let me just move that down so you can see what the theorem says again. That would be your diagram. Agreed? Okay? Derivative of the integral. The integral represents this area. Agreed? Now let's think about what this means. We're taking the derivative with respect to, are we? I think we're taking the derivative with respect to x, aren't we? Taking the derivative with respect to x. What does that mean?
How the rate of exchanges affects the area between the f of t and the t-axis.
Say it again.
The rate at which the area formed between the curve f of t and the t-axis, how it changes with respect to the change in x.
Yeah, that's a really good answer. That's a good explanation of that. Okay? Another way of saying that, see if you can finish this sentence for me. A small will
Give a small change in a with respect to t. No.
Yeah, okay. Right? That's what we talked about in first semester, right? What this effectively means, it's answering this question. A small change, an infinitesimally small change in x, will produce what change in area? Yes? So let's look at it geometrically. A small change in x means we're going to be over here somewhere. Let's assume that we're increasing x.